Okay, today's or this evening's exercise is to verify Newton's second law of motion, F equal ma. We're going to be using, and we'll use this for several exercises this semester, an air track. An air track, as I described in class, it's a hollow tube. This one is triangular in shape with a series of little air holes in it, and it's connected to a pump, and I can pump air through this. This is called an air cart, and it is machined, it's very smooth, and it's machined at the same angle as this track. If I turn on the pump and push the cart, the cart glides basically without friction. The whole idea is to eliminate friction. On top of this cart, I have a flag. We're going to use that flag to determine how fast this cart is moving. We're going to cause it to accelerate over a known distance, and then once the acceleration, as I described in class, the hanging mass has been removed, the cart will go through a photocell gate and trip a timer, which if Professor Schnall comes around on this side, you can see the timer. As I pull this cart through, you'll see that the time is running once the flag interrupts a beam of light, and it stops when the cart passes through the beam of light. If the cart is moving with constant velocity, and the driving force will have been removed at that point, if I know the length of the flag and the time it takes to go through the photocell beam, the light beam and the photocell gate, I know the time and the length of the flag, I can determine the velocity. Then I use Newton's second law to calculate what the acceleration should have been and what the acceleration actually is. The first thing we have to do is to make sure the air track is level, which I've already done. I need to know the mass. This is uppercase M. I have a gram scale here. I will record this data. It is 222.9 grams. Again, I will supply this data to you, and I have to measure the length of the flag. Now, I know this flag, if I put a vernier caliper on it, is 10 centimeters, but the way the electronics works, it doesn't see this as 10 centimeters. So what I'm going to do is push this cart very carefully by hand without the air on, and watch the timer and see when the timer just starts. And I'm pushing it very slowly, very carefully. I want to find out when the timer just starts. That means the flag has interrupted the beam. I'm going to look at the back edge of this cart, and it is at the 99.7 centimeter mark. I'll push it completely through until the timer just stops. I can slide the photocell gate out of the way. I'm now at 109.3 centimeters. Subtracting the difference between 109.3 and 99.7 gives me the effective length of the flag. Now I'll push this back where I started, and we're ready to go. We're going to put, and I've already have one set up, we're going to place, I'm going to use a slightly different cart, and I'll get the mass of that cart. We really should make sure we're using this cart. I'll use this flag, however. This cart and flag, we already know the length of this flag. This cart is 224.2 grams. So it's 224.2 grams is uppercase M. I'm going to place this on the track. You'll notice there's a piece of very light audio tape, for those of you who know tape recorders. And it goes over what's called an air pulley. So I reduce the friction, it blows air out and keeps the tape from rubbing. And it's attached to a little mass at the bottom and that is 5 grams, and I've already checked it. So what I'm going to do is pull this cart back here. The cart is, I'm going to, that's my 0 mark. When the cart is here, the small mass has reached the ground and the cart no longer is under acceleration. The book asks us to pull this back some 25 centimeters. So that's 10, whoops, I was using the rear range. 10, 20, 25 centimeters. What happens now, when I turn on the air pump, the cart will move, being accelerated while this mass reaches, till this mass reaches the floor. Okay. Stop the tape for a minute, Jerry. We'll have